So I'm going to talk
it's a life-taking thing.
Maybe once you move the slide, it will change. Ah, yes. Okay, very good.
Yeah, so Rafael and I are going to talk about optimization problems arising in invariant theory. So I'll explain all these things. And so the first part, I only
I think this is good.
I think so. It's very
Yeah,
quiet.
I mean, I remember a quote saying that it's it's easier to see a talk with a lit room than through closed eyelids.
I'm trying to shut the light down, but you think it's not too bright?
What does the audience think?
It's fine. It's fine.
It's okay. Yeah.
I don't like the light.
Okay, so so in the first part I'm only going to talk structural aspects, and then the second part I will talk about algorithms. I mean there is this term non-commutative optimization, so it's not kind of related to the title of the workshop, non-commutative analysis, but there are some intersections that I'll explain later. So here's a rough overview of this area. It's a new area. So here we study optimization problems arising from invariant theory. Describe what invariant theory is, and these optimization problems turn out to have a myriad of connections to several areas of computer science, mathematics, and physics. So here, just to list a few, there are applications in geometric complexity theory, quantum information, function analysis, optimization, complexity theory, and non-commutative algebra, and perhaps the two most important ones related to the topics of the workshop are the following. In quantum information, one can capture quantum machine problems in this language, and in non-commutative algebra, it captures the so-called free skew field and word problems. So I'll elaborate on both of these applications. And also, this area seems to suggest new avenues of convexity. So there's two new notions of geodesic convexity and also moment polyscopes that arise in this area. And since convexity is so much important in computational complexity, this also opens up new computational challenges. So here's a rough outline of the talk. I'll start with defining what invariant theory is, and then we'll see optimization problems in invariant theory. Then we'll briefly see what these moment polytopes are, and I'll So what is invariant theory? So the thing is as follows. So there's a group G. You think of maybe as GLN acts on a vector space V. Let's say a D-dimensional vector space V. What it means is that there's a group homomorphism from the group G to the group of D by D matrices, which satisfies the following. So for each group element little g in capital G, there's a linear map mg from V to V, and it satisfies the following properties. It respects multiplication with respect to the group operation. So mg1, g2 is mg1 times mg2, and identity is mapped to the identity. Okay. Sorry, this should be. So this is what it is, and just to see a few examples. For example, we have all seen these standard examples. The group Sn, the symmetric group on n elements, acts on the vector space Cn by permuting opinions. Okay. So it's one very simple group action. And another example is conjugation. The group GLN, n by n invertible matrices, it acts on n by n matrices by conjugation. So A sends x to Ax, A. So this is another action. So it's easy to see that it satisfies this problem. Okay. So this is the fundamental setting which invariant theory is based on. So any questions about this? About the group actions? Okay. So given a group action, there are various objects of study that you're interested in. The most fundamental one is something called invariant polynomials. So these are polynomial functions on the vector space which are left invariant by the action of the group G. Okay? So polynomials P such that P of MGV is equal to P of V for all group elements and vectors. So while this is very important in invariant theory, it's not what most of the talk is going to be about. So maybe if you don't understand, it's fine. So the more important notions for this talk are something called orbits and orbit closures. Okay? So orbit of a vector V is just the set of all vectors which the group action sends it to. Okay, so the orbit of a vector B is mgb for all group elements. So that's the orbit, and sometimes so we're in the Euclidean space, so you just take the closure with respect to the Euclidean. So yeah, so that's the orbit. It's just the orbit closure of vector B is just the closure of its. So any questions about these? What's the definition? Yeah, so there's many questions in theoretical computer science and across mathematics can be stated in terms of orbits and orbital closures of well-studied group actions. So in this talk, I'm going to focus on a very, very specific question about an orbital closure, something called the null cone. Yeah. Okay. So what is the null cone? So again, we have the setting. The group G is acting on a vector space V. So the null cone of this group action is a set of all vectors such that the zero vector lies in the orbital closure of V. Okay. So this is the null cone, set of all vectors V such that zero lies in the orbital closure of V. So in other words, there is a sequence of group elements G1 to Gk and so on, such that in the limit sends the vector to zero. Okay. So saying it again, there is a sequence of group elements which sends the vector to zero in the limit. And again, I mean, we can frame a computational problem given a vector V. It's to decide if it's in the null cone or not. And we'll see many examples of what this is. And for various group actions, this captures very, very interesting questions arising in various areas. Any questions about the question? So I would like to mention this one point. So this is an analytic definition of the null cone. There's a corresponding algebraic definition as well. So there's a theorem through Hilbert and Mumford. It says that a vector B is in the null cone if and only if all the invariant polynomials, all the homogeneous invariant polynomials P vanish on this vector B. So as with most theorems in mathematics, one direction of this theorem is trivial. Since polynomials are continuous, right, and the value of the invariant polynomials don't change by application of group actions. So if you apply the polynomial here, the value of the polynomial doesn't change, and when you take limits, it also doesn't change. So homogeneous invariant polynomial P has to vanish on a vector in the null cone. But the other direction is non-trivial, uses Kunst-Stebbins algebraic. Yeah, so this is the algebraic characterization of the null cone. And because of this analytic and algebraic interplay, something very interesting. Yeah. Okay. So now I'm going to mention various examples of group actions and what the corresponding null cone problems are. Okay. So this is the first group action we saw. Sn acting on Cn by permuting coordinates. In this case, the null cone is not very interesting. It just consists of a zero vector. I mean, the reason is that because we're acting by a finite group, so there are no closures. Orbit closures are equal to orbits. It's a finite thing. In fact, for all finite groups, the null cone is not interesting.
Can you go to the previous one?
Yes.
I just wanted.
Okay, so this analytic definition also is analytic. Yeah, so for all finite groups, the null cone is not interesting. The next example is the conjugation action we saw. G is n by n invertible matrices acting on n by n matrices by conjugation. So in this case, the invariants are generated by the following polynomials. So trace of x to the I, you can easily see that this is an invariant polynomial under this group action. And yeah, in fact, you can also prove that all the invariants can be written in terms of these simple invariants. So because the invariants are this, and the null cone is the vanishing of all the invariant polynomials, it means that the null cone for all this group action is all nilpotent matrices. Yeah, so it captures a very fundamental thing in math. But simple group action, the null cone captures a important. Okay, so here's another group action. Now the group is two n by n matrices, but with determinant 1. So this SLN is the group of n by n matrices with determinant 1. So we have two such groups acting on n by n matrices from the left and the right. So So A comma B sends X to AXB. So there's a group action. In this case, you can prove that there is actually only one invariant. So we know that determinant is one invariant of this group action. If you multiply on the left and right by determinant one matrices, the determinant doesn't change. And in fact, all the invariants are captured by this determinant polynomial. So all the invariants can be written as polynomial of the determinant. And hence the null cone is the set of singular matrices. Questions?
So don't you need b to the minus 1 if you want it to be a production?
Yeah, sorry, yeah, so yeah, for technicality we want either an inverse or a transpose. Yeah, okay. Yeah, so the next example is something more interesting. So here we have the same group action as before, but we restrict to diagonal matrices. So here STN is the group of n by n diagonal matrices with determinant 1. And then we have these two matrices acting the same way on n by n matrices by left and right multiplication. So what is the null cone in this case? So first of all, it's not hard to prove that all the invariant polynomials can be generated by the following matching monomials. So what is this monomial? Take any permutation sigma of Sn, and then you multiply, take a product from I to n of xi sigma. So basically, when anything in a matrix, you take the products of all the any generalized diagonal. So yeah, so this is not hard to prove. All the invariants are generated by this, and hence the null cone captures the perfect matching property. So what do I mean by this? So let's say you have a graph, H, a quadratic graph. You take its adjacency matrix AH, then AH is in the null cone if and only if this graph has no perfect matching. So yeah, by the way, so perfect matching is just a set of edges such that the degree of every vertex is exactly. So each vertex here is matched to some other vertex on the right hand side. Yeah, so in this case, null cone captures the perfect matching. So this matrix is in the null cone if and only if H has no perfect matching. And in fact, in this case, the entries of the matrix itself don't matter. The null cone is characterized by just the support pattern of it. So a general matrix is in the null cone if and only the support has no perfect matching. Okay. Questions? Yeah, so the next example is a very wide generalization of this example. Okay, yeah, so here we have again a commutative group of diagonal matrices. So Tn is the group of n by n diagonal matrices, and it acts on polynomials. So yeah, I mean there's a slight technicality. You have to take something called Laurent polynomials. So what this means is just that the exponents can be negative. Things like x1 to the minus 1, x2 are also. So G acts on this vector space of polynomials by scaling the variables. Okay? So it's a very simple group action. So let's say you have a group element T. You can write it as diagonal matrix T1 to Tn are the diagonal entries. Then this acts on this polynomial Q by sending Q to a scaled version of it. Okay? So the variable xi is multiplied by Tn. So Q of x1 to xn is set to Q of T1 x1 T2 x2 x2. Very simple group action. It just scale the variables by the diagonal entries. Right? So in this case, what is a null cone? So let's say I write Q as sum over alpha C alpha x alpha. Okay, so alphas are the exponent vectors. These are the coefficients. I'll define the support of Q to be all the exponent vectors where corresponding coefficient is non-zero. Then it turns out that in this case, the null cone captures the linear programming property. Okay? So the polynomial, so what do I mean? So polynomial Q is not in the null cone if and only if the zero vector lies in the convex hull of the support of Q. Okay? So Q is not in the null cone if and only if the zero vector lies in the convex hull. So this is something just true, follows from not so hard calculation. Okay? And this captures the linear program.
It's not in the null cone. 0, 5 is in the convex.
It's yeah, it's not in the null cone.
What topology are you using now?
Because now you've got
infinite dimensional vector space. So what do you mean that the vectors converge to 0?
Yeah, so when I talk about this vector space, I restrict the degree in some sense. Let's say the total degree of all the.
Okay, so then it's just.
It doesn't finite. Let's say degree bounded by D. Yeah, so Q is not in the null cone if this thing is. And this is a general linear program. So yeah, so already the commutative case captures like one of the most interesting computation problems. Theoretical computing. So then for non-abelian groups, the null cone membership problem can be seen as some kind of non-commutative analog of linear. And yeah, and so that's why it's very interesting to design algorithms. And yeah, while we have some algorithms, but in general this null cone problem for non-commutative groups to design a polynomial channel. Okay, any questions?
Quick question. Is that the same as Farkas' lemma in linear programming? It's a
This is
geometrical.
essentially Farkas lemma.
Okay.
Essentially.
And omega, sorry, I think you said this. Omega is just the set of possible exponents?
So this omega?
Yeah.
Yeah, this I just mean that you restrict the degrees in some sense. So omega
Oh.
could be like the total degree is bounded by D or something.
Okay, thanks.
Some finite set. Okay, so far, yeah, so we see that the most general, in fact, so yeah, so I should mention that this is in fact the most general commutative group action can be. Any commutative group action can be written like this. So yeah, in this case, null cone is exactly in program. So in the next slide, we'll see the first non-trivial example of a null cone problem for non-commutative groups. And this is the example connected to one of the main themes of the workshop. So we had this action of two n by n matrices on n by n matrices by left-right multiplication. Now we take the same action but on multiple matrices. Okay? So it's simultaneous left-right multiplication. So B comma C send a tuple of matrices x1 to xn to bx1c and so on bx1c. So you simultaneously pre and post multiply by b and c. So that's a group action. So yeah, in this case it requires non-trivial math to find the invariant polynomials. So this was done in this series of papers, and they proved that the invariant polynomials are generated by things of this form. Okay? So you take matrices d1 to dm of some dimension, but the same dimension d, and then you take the determinant of sum over I di tensor x. So yeah, I mean it's not hard to see that this thing is an invariant for this group action. Again, the b and c will just factor out, and the determinants are 1. But yeah, in fact, all the invariant polynomials can be written in terms of these kind of polynomials. And in this case, the null cone problem captures something called non-commutative singularity, and so this is from non-commutative algebra. In the complexity side, captures non-commutative rationality test. So I'll elaborate on what this means.
So just to understand, so this is tensor product di tensor product with xi.
Yes. Sum over I, di tensor xi, and then you take the determinant. So this is a polynomial in the entries of this matrix is x.
What are the DIs? So do you have bounds on the degrees or on
There are
size?
there are very good bounds on the degrees, like
on the size.
on the sizes, on the degrees of this polynomial in the size of dx, like essentially linear now.
So I'm just also confused a little bit. So this is supposed to be okay. So maybe I'm just this is so do you need the dimensions to match up? So you're summing it up and taking the determinant. So
Yeah, so the dimensions of across all i's of the d's should be the same.
I see.
Yeah. So you fix a dimension d, and then you take all d by d matrices di, and then you take.
Okay.
Yeah, and there are very good bounds on the dimension of the matrices which are required to generate the invariants. Now they are like polynomial in the dimension of these matrices.
And can I have a subset of matrices which does the job, which are not all of them? I mean, to have some nice generators, or
There's no nice generators, so a small random set would work.
Oh, right.
But
Yes.
producing an explicit nice set, deterministically it's okay. Producing a nice set.
okay.
Yeah, and for this non-con problem, there was a series of papers joined with Gurvitz, Rafael, and Harvey. Testin, Dagson, Ivanush, Kyao, Subramaniam. So these papers gave deterministic polynomial time algorithms. Test the null conjugate for this group action, and in fact, the main motivation was this problem from non-commutative algebra. So describe in the next two slides. And yeah, so the problems, the algorithms in this paper are analytic, they're motivated by the optimization approach, and the algorithms in these papers are combinatorial. Okay, so yeah, what is this non-commutative problem? Yeah, so this notion of non-commutative rational expressions, which I'm sure we'll hear a lot more about in the succeeding talks. So let's say you have m variables, x1 to xm. The non-commutative expressions look something like this. So the variables x1 to xi are non-commuting, so there's no easy canonical form to simplify these expressions to. So if these variables were commuting, you could always write these kind of expressions as the ratio of two polynomials. But when they are formally non-commuting, there's no way to simplify these, and in fact, they could exist expressions with unbounded number of nested inversions. So a more pictorial way of representing these expressions is as formulas. So at the base leaves you have either constants from the field f or variables, and then you have various gates, like product gates, addition gates, and inversion gates. So you can slowly build up these rational expressions in terms of these formulas, and that's going to be input to the algorithm problems. Yeah, so these are non-commutative expressions. Okay, so any questions? Yeah, these are just simple formulas. And then
The diagram doesn't correspond precisely to the example.
so yeah, this diagram is not this diagram is not supposed to compute this.
Different expression.
Yeah, so then this computation problem is given to non-commutative rational expressions. Do they correspond to the same thing or not? So that's the computation problem. But yeah, what does it even mean for two expressions to represent the same element? Because there's no easy canonical form. If they're commuting variables, you could just simplify them to the canonical form and check if they're same or not. But what does it mean for two different non-commutative expressions to mean the same element? So Amit Sur in 1966 gave this operational definition, which is as follows. Yeah. So yeah, first of all, I need a definition. So given a rational expression R in m variables, something like this, I'll define the domain of this rational expression as a set of all matrices T1 to Tm. So again, all the T's are of the same dimension, D. So all matrices T1 to Tm such that this expression is defined. So let's do an example. Let's say this is the expression. x1, x2 is x1, x2 minus x2, x1 inverse. And the domain is a set of all matrices T1, T2 such that the determinant of T1, T2 minus T2, T1 is non-zero. Yeah, so I mean, you should be able to take the inverse when you plug in the matrices. So that's the domain. Basically, any inverse that you're taking is well defined. So that's the domain. And then two rational expressions are equivalent if they evaluate to the same thing on their domains. So R1 and R2 are equivalent if R1 of T1 to Tm is equal to R2 of T1 to Tm for all the matrices T1 to Tm in the domain, intersection of the domain. So it's an operational definition. You plug in on all matrices of all sizes and see if they give the same result. Yes?
But the domains don't need to be the same for them to be.
The domains don't need to be the same. Yeah, in fact, there's a subtle point which I am avoiding here. You only define it, these equivalence for rational expressions whose domains are non-empty.
So
And in fact, if a domain is non-empty, then it is dense.
So think of x1 times x1 inverse. That should be the same as 1, but it's got a different domain.
So you said the domains have to be not empty, or their intersection has to be not empty?
The domains have to be non-empty. If both the domains are non-empty, then the intersection is also non-empty. Basically, if a domain is non-empty, then the domain is dense.
Okay.
If you take large enough matrices. Okay. I mean, similarly, for example, if you take a polynomial, it doesn't vanish or something, then the domain is dense.
So maybe is it obvious this is an equivalence relation? It says that it's transitive.
Yes, yeah, density arguments.
Yeah.
I guess the density is.
Yes.
Okay. Yeah, I mean, yeah, there's a non-trivial thing here. I mean, okay, this thing succeeding talks will cover. So this, yeah, you can define these equivalent sets, and then the equivalent sets form a skew field. It's called the free skew field. So that's a non-trivial. But yeah, not important. Okay.
Maybe just a little historical remark. This is not exactly Amitzur's definition.
Oh, this is not.
So Amitzur was not testing on matrices. Amitzur just took an arbitrary large division ring, large minimal meaning infinite dimensional over its center, over an infinite center, and tested on that.
Okay.
And his theorem was that it doesn't matter which division ring you take for testing. And then it's a easy variation on that, which became popular in the last 10 or 15 years, that instead of taking an abstract arbitrary large division ring, we actually test on matrices of all sizes over our ground field.
Okay. Sorry, thanks. Okay. Yeah, so the non-commutative thing is given two expressions, are they equivalent or not? So this, I mean, you can easily say the same as given a rational expression is equivalent to 0. And yeah, so this problem reduces to the example 6, the null problem for the example 6 problem that I mentioned. And previous algorithms for this problem required exponential time. And I mentioned these references which gave polynomial time algorithms for this problem. Okay. And yeah, so the connection to invariant theory is very crucial for designing this efficiently. Okay. Yeah, so I should mention one thing. So for now there are very simple algorithms. If you allow for randomness for testing these problems. Okay, yeah, so if you have this rational expression, let's say the number of nodes in this rational expression are S, then the theorem of Dirks and Naka, proven in 2016, says that it suffices to test for matrices of size S by S. Okay? So an easy algorithm, randomized algorithm for this problem now is that you just plug in random S by S matrices and test if that rational expression very good. So it suffices to plug in random S by S matrices, where S is the number of nodes in this rational expression. But if you want deterministic algorithms,
This is the number of what?
sorry, S is the number of nodes in this
In the circuit.
Sorry,
What's a node?
like these leaf nodes and the number of gates.
Number of gates, okay.
Yeah, number of size of this. Yeah, so there's an easy randomized algorithm, but if you want a deterministic algorithm, the algorithms are quite easy. Okay, so any questions so far?
Could you please comment a bit on how this reduces to example 6? I didn't get this.
Yeah, so this reduces to example 6. So there's a theorem of Kohn that if you have a rational expression, then you can write it as the inverse of. So if you have a rational expression R of x1 to xm, then you can then there exists some matrices A1 to A which are of size S by S. Such that R of x1 to xm is the inverse of these of the matrix, somehow IXI AI, and the 1 1. So basically, you can design a matrix whose entries are linear polynomials in the x's. Take the inverse of the matrix, and the sum entry of that inverse will be this rational expression. So yeah, this is due to Kohn in 1970s. So this is the non-commutative analog of Bayes' theorem in complexity. So for complex series, it says that any polynomial can be written as the determinant of some matrix. But yeah, I mean this is more general and was proven before Bayes. And so given this, to test R is 0 or not, can be reduced to the problem of testing if this matrix, not this, some related matrix is invertible or not. So this invertibility is defined over the fuse field.
Are there blackboard lights?
Can you turn on the light in the front?
Yeah,
Very hard to see.
yeah, I think these formulas are gonna come up in other talks, so it's good to kind of how this works. You can tell, there we go. Is anybody in the back seat? It's written pretty small,
Sorry.
so
Yeah,
they're writing small on this blackboard, because everybody, it's such a long room.
Okay, let me just say, so this rational expression testing with 0 or not can be reduced to the invertibility of some matrix whose entries are linear forms, and this invertibility we find over this equivalence classes. And this problem is what that example 6 was captured, right? Because we were plugging in this by matrices.
Does everybody understand this? Can you see it? That's the formula that keeps coming up over and over again in other lectures, so.
Sorry, one question. I'm a bit confused about that. That produces an equivalent expression to the one that you have, right? But you cannot guarantee that it will get you the same expression.
It gives an equivalent expression, yeah.
So how do I know that I can construct a matrix H5? Or how?
You're saying it's not trivial to prove this theorem because
No, I'm not saying the proof of the theorem. I believe the theorem. What I'm trying to understand is how does one use it? Because somehow
how does one use this?
right. If I have a given expression, right?
Yeah, if you have a given expression, so this can be reduced to by a simple manipulation, but to testing if a matrix is invertible or not. Basically, testing if some entry of the inverse is 0 can be reduced to testing if some matrix is invertible or not. And that invertibility problem was what example 6 captures.
Now, the way how you get this matrix is how you get that linear matrix. I mean, it's like how expression is built, as you said, like it's sum of something and then you just go step
It's a
by step.
realization algorithm
Yeah,
or whatever. Yeah, but I guess what I'm confused is that somehow that in there that's just an equivalent, right? You prove it's not that you get exactly the same expression, you get an equivalent expression.
Yeah.
Right?
They'll agree on the dense set.
Yeah, sure.
Yeah, so equivalence is what we are testing anyways. We're trying to test if some expression is equivalent to 0 or not.
I guess what I'm confused is that somehow you're trying to produce an expression that it's equivalent and you will prove this about the equivalent expression, but you don't actually know that it's equivalent to the one that you have.
When you say equivalent, I think you actually mean equality, right? Because it keeps building operation of it, like the one on entry is exactly the same expression. It's not
this equality
equivalent.
is equivalence, yeah.
So in the example that you had before, right, that 1 is x inverse. If I give you x inverse, right, I will not be able, that construction will not give you x inverse, will give you 1. Right,
It's not clear what it will produce. It might produce x inverse or 1 or some other expression equivalent to x inverse. Yeah, so there's some tricky things like this. Yeah, this free scoop will maybe be covered in later talks. But yeah, so this is just a rough outline. So the 0 can be reduced to testing invertibility of matrices, and that is what example 6 would catch. Yeah, maybe we can talk more.
Sir, just one question. So those AIs that are S times S, is that the same as that was the number of nodes starting in
Yeah, so-
or almost the same as?
Yeah, these are roughly, yeah, maybe not exactly S, but the number of nodes is S, maybe this is S plus 2 or something like that.
Okay.
Yeah, so it's very efficient in terms of number.
And maybe just another small comment to put your mind more. It is you always can arrange for this realizational linearization to have domain containing the domain of the original expression.
I see. That's
If you're a little bit careful, and it's kind of usual network synthesis.
Okay, so yeah, so let's see what are the optimization problems arising in this business. So yeah, this viewpoint is of geometric invariant, which uses analytic and geometric tools to study the problems of invariant. Short GIT. Yeah, so what? Yeah, one fundamental question is what is the complexity of null cone membership? So geometric invariant theory puts in an NP intersection QNP model. So there is something called the Hilbert-Mumford criterion I won't go into, which satisfies which shows how do you certify membership in the null cone. And there's something called the Kempnes theorem, which satisfies how do you, which tells you how do you certify non-membership in the null cone. And this is the one I am going to focus on. Yeah, so Kempnes. So again, we are deciding a group G is acting on a vector space. How do you certify a V is not in the null cone? That is, how do you prove to someone that the vector V is not in the null cone? So one way is you just give an invariant polynomial P which doesn't vanish on vector V. So this will prove that the vector V is not in the null cone. But this approach, this is by the algebraic characterization of the null cone. So this approach is not feasible in general because invariant polynomials are very hard to find. They can have exponentially high degree and they will have exponentially high complexity to compute them and so on. So even if someone gives you an invariant polynomial P, it won't be clear how do you evaluate the invariant polynomial P on the vector. So this approach, the algebraic approach is not feasible. The analytic approach will give us a alternate efficient way, and that is captured by this Kempnes theorem. Yeah, so to state the Kempnes theorem, I need this optimization perspective on this null cone problem. So the optimization problem is finding minimal norm elements in the orbit closures. Okay? So it looks something like this. So you have this orbit closure of a vector V, and you want to find the element in the orbit closure of minimum norm. So this is the optimization problem which captures this. So you fix a vector V, then you take infimum over all group elements of the norm of MGV. So this is the optimization problem. And it captures the null cone problem in the sense that null cone is just set of all vectors V whose capacity is Z. So we can study this more general optimization problem to understand the null cone. So any questions about the optimization problem? You just minimize the norm, which is just the gradient of this optimization problem. So given vector V, I can define this function fb of g, which is the norm of mgb squared, and then the moment map is just the gradient of this function at g equals identity. So basically it's trying to capture how much the norm of V decreases if we act by infinitesimal actions around identity. So you take small perturbations of the identity element in the group and act by that, and how much the rate of change of the norm is what moment map captures. So yeah, I won't formally define this, but let's see one very simple example. So let's say you have the group which is just a group of as non-zero complex numbers acting on complex numbers by multiplication. So in this case, the function is just norm of t squared v squared. The moment map will consider the action of numbers around 0. So you consider the action of exponential of s, where s is roughly 0. It's a real number roughly 0. And the moment map is just the rate of change of the norm when you act by this exponential of s. So d by ds of exponential 2s v squared, this turns out to be 2s. So in this case, the moment map is just a number, the norm square of the vector. In general, the moment map sends a vector v to the Lie algebra of the group that is in.
Okay, so I'm confused now. Why did we say that the moment map? how does G acts on V by just scaling, right?
Yeah, yeah.
So how did you get to this exponent?
Exponent.
For the T.
It was just a rewriting the, you just wanted to write T as e to the s?
Yeah, so I mean, we are acting by groups. So the most natural way to take derivatives of gradients is by this parameterization. Basically, any group element can be written as e to the sum matrix.
I see, because you wanted anyway, group elements should be non-zero, so
Yeah.
you might as well just write them as e to the s,
Yeah.
and then, okay. So, in some sense, maybe you could have said, that, okay, your group is the additive group, and it acts on V by pi of s of V is e to the s times V.
Yeah, so yeah, in general, the Moon map is the gradient and it sends a vector V to the Lie algebra of the group. So yeah, it's not related for this talk. So, yeah, I did another example from the VLC. This one. Yeah, sorry, I want to just try to skip the slide. It will take some time. Okay. Yeah, so then what is the Campness theorem saying? It says that a vector V is not in the null cone if and only if there exists a non-zero vector W in its orbit closure whose moment map is 0. Okay? So V is not in the null cone if and only if there is a non-zero W in its orbit closure such that the moment map of W is 0. So in this way, the vector W certifies that V is not in the null cone. Okay. So one direction of this theorem again is easy. So it goes as follows. So basically, it's a phenomena in optimization that a global minima is a local minimum. So the vector V is not in the null cone. We take the W vector of minimal norm in its orbit closure. Since V is not in the null cone, W is non-zero. And since W is minimum norm in the orbit closure of V, it is minimum norm in its orbit itself. Hence, the norm of W doesn't change if you act by infinitesimal actions around that entity. So hence the moment map is 0. So yeah, even if you don't follow this, it's just a simple thing that a global minimum of an optimization problem is also a local minimum. So this direction is easy. The other direction is the more interesting one. The other direction is saying that a local minimum is a global minimum. So since this theorem is true, there has to be some notion of convexity underlying all this. And for commutative group actions, it turns out just to be the normal Euclidean convexity. Okay, you need to do a change of variables, it's exponential. Like you need to plug in t equals exponential in S, and then it becomes convexity. Okay? And that convexity implies this theorem. For non-commutative group actions, something much more interesting happens. There's a notion of underlying convexity called geodesic convexity, which I won't have time to talk about. Rafael will talk about it some, and there's also a talk by Surit later in the workshop. We're talking about this different notion of convexity.
So in particular, is it the case that if you do gradient descent according to, you do gradient descent on the capacity, then you reach, if it is in the null cone, you'll reach 0?
Yes. Yeah, so yeah, file can analyze some gradient descent.
But I'm a little bit confused because you said it was an NP intersect co-NP, and you didn't say it was efficiently solvable.
Yeah, so there are bit complexity issues that arise, and we haven't been able to analyze these bit complexity issues. So, for example,
Eventually you will reach 0, but maybe that not in polynomial number of steps.
Yeah. So so to certify that V is not in the null cone, you want to give this W, right? And the moment map of W is 0. So to make W could have irrational entries and so on. So you want to discretize it, and the moment map will be approximately 0 and so on. And then to prove it's in the orbit closure, you want to give the corresponding group element that sends B to some approximate W. So you need to bound that to bit complexity of the entries of G and so on. So that is something it's not clear currently. But apart from the bit complexity issues, this is okay.
there's no rush. I mean, depends on people's capacity for wearing out and so forth. I mean, we could take a 5-minute break and come back and you could continue, and then after that, I mean, there's no reason to.
I mean, it depends on you, like in some sense, what's the right point for you to stop?
Well, I guess they've planned it, so I'd say there's no rush, basically. What happens is that after the next talk, there's a 45-minute break. So there's a 15-minute break.
Yeah,
So rushing is not good.
So yeah, this is a completely new topic, not new topic, but related to this thing. So maybe let me just not go into the details, but just mention. Yeah, so there is this movement maps, and then there's this polytopes that arise from group actions.
So what was the moment map again you've been talking about? My mind wandered at some point. It was mu G denotes this moment map, and it's the sum of the coefficients times.
The gradient F is the capacity.
So yeah, this is in this specific example.
Okay.
We can talk. But yeah, we can talk about things. So yeah, for commutative group actions, you can explicitly compute what the gradient is. Let me not go into this. But I'll just mention this specific example relate how this thing relates to quantum information. So yeah, so let's say you have a pure quantum state psi on a D quantum system. Okay, so this is a vector in a direct tensor product of complex vector spaces. So if you have a pure quantum state on D systems, you want to characterize the marginals on the various subsystems. Yeah. So sorry. Yeah, I'm going to. Yeah, if you know what this is, yeah, you can follow it. So, so you want to characterize all the margins on the single systems that arise, and only the spectrum of these systems matter because the rotations are 4 feet. And in terms of the collection of all such spectra forms a convex polytope. This is called the movement polytope, and this arises from studying the group action of products of GLs and tensors. And we have efficient algorithms by various methods for these problems, alternating minimization, geodesic gradient descent, and so on, which Rafael will talk about some. And the main thing is that all these algorithms that we have for these problems run in time polynomial in 1 over epsilon, where epsilon is the error parameter. And the main challenge is designing algorithms which run in time scales like log 1 over epsilon. Right? So basically you want to handle errors which are exponentially small than dimensions and so on. So that's the main challenge in this areas. More examples, polytope, Shooter polytopes. There are some combinatorial polytopes that also are captured by this thing. Yeah, so we can talk offline about these movement polytopes. Let me end in terms. So the most important problems are complexities of this null cone membership problem and also moment polytope membership, which I didn't define what it is. Is it in NP intersection co-NP? We saw that morally it is, but proving the bit complexity and so on, it's open. And finally, you would want to design polynomial time algorithms for this problem. And the main thing is that all the first order methods, like gradient descent and so on, in the worst case, they only give you poly 1 over epsilon kind of guarantee running times where epsilon is the error parameter. And you want to define a design algorithm which scale like log 1 over epsilon. And in the Euclidean convex case, these are given by either the ellipsoid method or interior point methods. And so the main question is how do you design these methods or generalize these methods to geodesically convex problems. So that's the main challenge in this area. And of course, there's some very beautiful ways in which convexity arises in these problems, and it ought to have more applications. And if you want to learn more about these topics, there was a workshop at IIS in 2018. All the videos are available. It was a lot of beautiful talks. And also, Avi Bisson gave a tutorial in CCC 2017 on a subset of these topics. Yeah, okay, thank you.
Question? So any questions? Not questions.
So,
Eric.
you said about the poly 1 over epsilon. Do you know? I mean, that's your upper bound, but do you know that it actually converges that slowly?
Yeah, so the very simple examples where they converge. Okay.
Further,
Yeah, so one thing, I mean, in the worst case, they will convert very slowly. But if you take typical instances, they usually convert very fast. So if you take random instances and code them up, then they convert very fast. But you can design instances where they convert.
And this is the thing where you don't know you get polylog 1 over epsilon. Is that a general thing about geodesically convex optimization? I mean, or is it specific to the?
It is a general thing in the sense that we don't have algorithms which run in time polylog or epsilon for, in general for geodesically convex optimization. For convex optimization.
further question? Yeah, I guess I must confess a few facts. I didn't understand one slide with several slides, but I kind of passed toward the end. So we had a, yeah, that one. So one thing I should say is that we don't really have to start the next talk on time. I mean, I don't know what the other organizers. I represent California culture. Yeah, so we're San Diego culture even. We're 40 miles from Mexico. That's nice like that. So the yeah, so do this slide.
Okay, yeah, I'll do it more slowly.
Yeah.
So yeah, so yeah, states of quantum systems are characterized by pure quantum states are characterized by basically. Yeah, so this will be a.
Right, big.
Yeah, basically this state will be a vector in CD1 tensor CD2 where D1 to so you have D quantum systems, each of dimension n1 to nd, and this pure quantum state basically is a vector in the tensor product of these things. Then you have this group action. So let's say you have the group GLN1 product GLN2 product GLND acts on this vector space. Basically, each product acts on each tensor product. The action is, for example, A1 AD sends U1 tensor UD to A1 U1 tensor A2 UD. So it's a very natural group action, and you can extend this linearly to the whole vector space. So this group action, if you apply the theory which I did mention, the theory of movement polytopes, this captures the quantum marginal problem, the one-body quantum marginal problem. And what is this one-body quantum marginal problem? You describe states of systems of you describe the states of the individual systems. So these are density matrices, which are PSD matrices of trace 1. So this will be in Mn1 C and so on. So these are PSD matrices with trace 1. Given these, which describe the states of the individual systems, is there a global state which captures this or not? That's the problem. So given rho 1 to rho d, is there a global pure state that captures these marginals? That is the one-body quantum marginal problem, and that that comes from this theory of convex polytopes, moment polytopes.
What's it mean to say those are marginals of a single state?
Yeah, so just like you have, let's say you have a probability distribution of two random variables. That probability distribution induces marginal distributions on each of the random variables. Similarly, if you have quantum states on many particles, it induces marginal states on various subsets of particles.
By what formula?
By what formula? Yeah, so there is a formula. Yeah, there is a formula.
Oh, okay, so it's not
Yeah.
not been presented, so
Yeah, it's not even present. Yeah, so this is something standard in quantum information. I mean, just like there is some natural way which captures it. So one way to define it is that if you do operations on only subsets of the systems, it should be captured by just the marginal states of the systems. You should be able to compute what the operation will do just by the marginal states. Yeah, so there's an explicit formula that defines it, but it's a very natural operation. And yeah, so for this problem, you can design efficient algorithms, this polygon or epsilon, using this theory, using this theory. Yeah, so more questions on this? Yeah, I think if you haven't seen this, it might be tricky to say one.
More questions? Why don't we take a 7-minute break or something like that, get some coffee, come back. We're running 5 minutes late. Let's finish. So it's a point of honor, we have to run late. It's not even an informal meeting.
I think probably your handwriting is better than mine regardless.